Welcome back, ladies and gentlemen. This short video is going to prepare you to do your homework for practice C in Chapter 11. And here we're working with mass spring systems. So I want to show you an example of a mass spring system. And this page I'm looking at here is your chapter review page. So we have the equation of the force of the spring is equal to the negative force spring constant times the distance that it stretched out. And in the last video, we did the period for a pendulum, also simple harmonic motion, 2 pi times the length of the rope or string divided by the acceleration due to gravity. In this case here, we also have a simple harmonic motion. Picture a spring attached to a mass. So I got this box attached to a spring and I stretch it out and let it go, and boing, boing is going to go back and forth. A period is from one place where it was back to that place again. So let's say the unstretched point, stretch it out and it goes past it, comes back to that unstretched, that would be your period. So the period here, here's your formula, is 2 pi times the square root of the mass, how much mass that object you have to it, divided by the spring constant. So it depends on your spring and the mass of your object, not the length of the spring. And just so you see the units, mass is obviously kilograms, but the spring constant turns out to be kilograms per second squared. And I'll show you that when we do the problem. Before we do that, I want to show you an example using a simulation. Let's see if this converts over. Here we go. All right. So what we have here is we have on the left side, we have a spring, and on the right side, we have a spring. I have the ability to change the spring constant. So let's say I make it really large. Notice how it's getting thicker. And so you can play with this. I'll send you a link to this. You can play and see how much it's not going to stretch out as much, or will it stretch out even more. And over down here, I have some different masses. So I'm going to start with the 50 gram and hang it onto here. And you have to press play. And there it goes. So we also have frequency and period here, depending on how long it takes to come back to its original position. Let me slow this down. The furthest it stretches, that would be your X, okay? And you have your spring constant depending on this, and you'll have a force from your equation, F is equal to negative KX. All right, now notice that it comes about this far. Let's see if we can memorize that. I can't mark it. And now I'm going to stop it, and I'm going to change it to, oh, I should have made the same spring constant. Let me move this spring constant about the same place as the other one. On the other side, and I will change it to double, 100 instead of, and let's press play. So you may not be surprised that the 100 gram one is going to go stretch out a lot farther, okay? But notice that it's taking a different amount of time to go back to its original position. So here you notice that the period is not the same. All right, to make it really pronounced difference, I'm going to change the 100 gram to 250 grams. Obviously, with 5 times heavier mass. Now let's take a look at it. First of all, it's going to get stretched out a lot farther. All right, now this can be changed if I change the spring constant, make it harder. But you'll notice that the period is not exactly the same amount. All right, so I'm going to stop that. And to prove that to you, I'm going to make sure that they both have the same mass on it. 100 grams here and 100 grams on the one on the right. And I really want to make sure they have the same spring constant. So I'm going to put them both on the same mark. That looks like the same mark. All right. I'm not quite sure if that's exactly the same mark. Let's see. All right. So they're a lot more similar. I'm thinking the spring constant's not exactly the same in these cases, but you see that the period is a lot more similar to it. All right, so let's take a look at the homework. I'm going to stop this and we'll move to my desk, my table here, and we'll read the problem. All right, here we go. It's number 21, and it's also page 397. There it is. It says, let me make it bigger. It says a spring with the spring constant of 1.8 times 10 to the second power newtons per meter. And that's what it should be. How many newtons does it take to go a whole meter is the units for a spring constant, is attached to a mass, 1.5 kilogram mass, and then set into motion. What's the period of the mass spring system? And what's the frequency of the vibration? So here's my little picture. I have a spring. The spring constant is 100 Newton per meters, and the mass is 1.5 kilograms. And so the question they're asking is, what's the period? And what's the frequency? Now, hopefully you learned by now, you did the con, that they're just reciprocal of each other, right? That the period is equal to 1 over the frequency, and the frequency is equal to 1 over the period. Once you have one, you know what the other one is. All right, so let's take a look at the equation for a period in the mass spring system. We have the period is equal to 2 pi times the mass, square root of the mass over the spring constant. That's all we have to do. We have to just plug that in. But let's make sure that the units work. I'm going to prove it to you. All right, so here I have equal to 2 pi times the square root of 1.5 kilograms, 1.5 kilograms, and I have to put K, which is 100 newtons per meter. Well, I'm not going to get units to cancel out that way. So let's write down what a newton is. We know that a newton is a kilogram meters per second squared. That's what a newton is. And then we have to divide that by the meter. Divide that by the meter. Well, now you see that your meters cancel out, and you end up with kilograms per second squared, which is why it said that on your handout, summary of chapter 11. So we can put down 180 here, kilograms per second squared. So my kilograms cancel out, and I have second squared and the second squared downstairs in the basement of the basement. So why does that end up being on the top? Well, let's do a little review here. What is 1 over 1 over second squared? 1 over 1 over second squared, that's equal to 1 divided by 1 over second squared. Well, when you're dividing fractions, I'm going to make it 1 over 1. That's the same thing as multiplying. It's the second one's reciprocal, or either one of them's reciprocal. Second squared over 1. All right, so that's why it ends up being second squared. Okay, so that's good. I'll end up with second squared inside the square root. Well, when I square root it, I'll get seconds. Okay, so let's use our calculator now. Hear it? All right, here we go. I'm going to say 1.5 divided by 180. I'll make sure is equal to, there we go. We have that number there. So I want now to take the square root. I did the inside, now I need to square root that. So I square root the answer. There we go. All right, there's my square root. Now I need to multiply it by 2 times pi. So I say 2 times 2 pi. There we go. So I get 0.57357. All right, so what is that? 0.57357 seconds. Now I can worry about my significant figures. Looks like we only have 2 significant figures. So that's about 0.57 seconds. So that's my period. That's my period. That means that it took over half a second from some position back to that position. So maybe the unstretched back to that neutral equilibrium position. All right, so there's my period. Well, the frequency is just 1 over the period. So I leave that in my calculator and I say, please give me the inverse. You guys know that, x to the -1. Give me that. And I have 1.743. So the frequency is 1.7 seconds, 1.74 seconds. Now, what are the units? I'm sorry, not seconds, hertz. Hertz, it's 1 over seconds, hertz. So it's 1 over second, and the definition of hertz, 1 hertz, is, you'll see it sometimes as second to the -1 or just per second, per second. So it was able to go through 1.74 cycles per 1 second. So that's what that hertz means, okay? And that's it. So we just realized that the period for a mass spring system just has to do with the mass and the spring constant. So in your lab, you're going to be putting your cell phone in a baggie, and you're going to be hanging it See if I can unzoom here. And then you'll hang it from your little spring, and you'll see how far your spring will stretch out depending on the mass of your cell phone, your smartphone, which hopefully you'll get online for the exact model that you have. All right, so that's all I have for us right now. I'll see you next time.